Hello, today I am going to discuss about the design aspects of flexural member or beam member. Now, when we are talking about designing of beam member, different aspects we have to see. One is if beam is unsupported, it means lateral support is not there. Another is if lateral support is there. For laterally support and unsupported beam, the design philosophy will be different, because the compressive stress, allowable compressive stress for both the cases will be different. How it is going to differ, that we will discuss later, but today we will be focusing our lecture only on the laterally supported beams. That means the beam, when it is subjected to transverse load, how it is going to develop the stresses. Stresses means stresses due to bending, stresses due to shear and the deflection. So, when we are going to design the beam, what are the things we will check? First, we will find out the stresses due to bending, and accordingly we will try to find out the appropriate section modulus and then appropriate dimension of a beam section. And based on the availability of the member and requirement, we will choose some particular section. Then we will check for shear stress. Shear stress, whatever shear stress is developing, that we will check. Next, what we will do? We will check for deflection, because deflection criteria has to be maintained as given in the code, which we have discussed last lecture. Next, another aspect which we will discuss today is the crippling and buckling effect. Because of concentrated load at a particular section of the beam and at the support where the reaction force is developing in constant way, there crippling effect will come into picture. So, we have to see that the design section, whatever section we are going to adapt, whether it is okay for crippling effect point of view or not. That means the stresses due to crippling we will check, and then we will find out whether the member which we are going to adapt is okay or not. So, in this way we will try to design, right. So, now first we will see what are the aspects of design, means design procedure. Design procedure can be divided into three parts. One is structural effects, another is secondary effects, and then practical limitation. That means, when we are going for designing, we will see the structural things, means structural requirements, what is the things required. As we know, as I was telling, that it is required the bending moment. That means, what is the bending moment, and because of bending moment, what is the stresses, say sigma Bt or sigma Bc, where stresses sigma Bt is the bending stresses due to tension and bending stress in compression of the member. Then shear force, and for that what is the shear stress is developing and what is the limiting stress, and then we will find out whether it is okay or not. And then deflection, we have to check the deflection, maximum deflection what is developing in the member, then we will see whether it is violating the codal provision or not. And of course, stability, because stability is another criteria through which we have to see whether the member is stable or not. What are the secondary effects? Secondary effects, as you know, that is local buckling and secondary forces. Local buckling may come into picture, other thing is secondary forces due to buckling, it may come into picture. Another is connections. Connections also we have to see, and practical limitations also we have to look into matter, that is durability, like fabrication tolerances, erection limit, etc. So, durability, fabrication, tolerance and erection, all those things we have to see, right. Now, beam can be designed in different way. There are two design philosophy are existing. One is working stress method of design, another is limit state method of design. So, here limit state method of limit state design. Okay. So, as we know, I probably I can assume that you know what is the basic philosophy of working stress method of design and limit state method of design. However, I am just discussing little here, that is, in case of working stress method we know that the material obeys the Hooke's law. That means, stress strain relationship of the material obeys the Hooke's law. That means, stress varies as strain, right. So, Hooke's law which tells that stress is proportional to the strain. So, that means in case of working stress method we are going to take the value f y up to this, where the maximum strain is going to develop here. After that we are not, this portion we are not going to consider, though it can take some more load with some additional strain. But in our country, means in India, so far we have not introduced the limit state method of design in case of steel. In case of concrete design, we are well conversant with the limit state method of design, but in case of steel design, we are not using the limit state method of design. So far we are using working state method of design. So, here what we will see, that from this we can see that E is equal to sigma by epsilon, means E is the modulus of elasticity which will become sigma by E. So, this stress strain relationship we will maintain, that stress and strain is proportional, stress is proportional to the strain. So, this is varying linearly, this is linear. These assumptions we are using for working stress method of design. So, the maximum value of the limiting stress of the particular material we will consider here up to here, where the distribution is linear, where the curve is linear. After that we are not going to consider. But as we know, in case of limit state method of design, we are limiting the in terms of ultimate load, in terms of serviceability and other things, right. Basically, ultimate load method is what? Ultimate load method is like this, that after certain period also, say if I see taut steel, this will be something like this and then fail. So, up to this we are going to take the effect of deflection. So, this will become f y, right. But in case of limit state working state method design, we will take up to this, right. So, what we are seeing, in case of limit state method of design, the load carrying capacity will increase with the increase of some deflection. So, deflection also will increase with the increase of load carrying capacity. This is what we used to do, and of course, in case of limit state method design, what we have to ensure that serviceability condition and other things, that whether that deflection is okay from serviceability condition, whether the occupants will feel discomfort or not, all those things we have to check. So, which is called serviceability method, means service load, what will be the service load, all these things will come into picture. However, we are not going into details of those limit state method, we will be focusing our lecture only on working stress method of design. Here you see the members are primarily designed to resist maximum bending moment and checked for shear considerations, and finally detailed against local buckling and fabrication tolerances. So, entire design method will be based on this philosophy, right. I am repeating once again that the members are primarily designed to resist the maximum bending moment and checked for shear considerations, and finally detailed against local buckling and fabrication tolerances. Now, first we will discuss about the criteria for the design of bending moment. That means, if bending moment M develops in the member, then how we will reach into the a section, a particular dimension of the member, how do we reach, that we will try to find out from the bending moment point of view. As we know, bending moment, we can, means from bending moment we can find out the bending stress, sigma is equal to plus minus m by I into y, because if for a simple case, if we see, say this is a cross section, then we know that the stress will develop linearly, right, because working stress method of design we are using. So, we can say that sigma will become m by I into y, and here if we consider the top, we can say sigma t, and this we can say sigma b. So, sigma t and b will be say plus minus m by I into y, where y is the distance from neutral axis, right. So, in this way we can find out sigma is the bending stress. So, we are considering plus in tension and minus in compression, or different, means or the reverse also we can consider, it is up to us how we are going to assume that whether compression we are going to consider as plus or minus, right. I is the effective moment of inertia of the section and y is the distance of the fiber from the CG where stress is computed. Means if we compute the stress here, then say suppose we have computed stress here in this section, then we will consider y is this, like this, and then this has to be less than the allowable bending stress, right. So, bending stress whatever we are going to calculate, that has to be less than allowable bending stress, right. Now, as we are telling that calculated compressive stress we can say sigma c and tensile stress say sigma t. So, sigma c I can write m by I into y t, that means say if cross section is like this, means stress distribution is like this, then here we can assume that this is sigma c compression and this is sigma t, it is developing sigma t, right, and say this distance is say y t at top flange and this is say y b distance at bottom flange, right. So, this is a member, right, neutral axis is here. So, what we are calculating, that sigma c will become here as m by I into y t, right, and I by y t can be written as z t. So, m by z t and it has to be less than sigma b c, where sigma b c is the allowable bending stress in compression. Similarly, sigma b t will be the allowable bending stress in tension, right, and calculated stress, bending stress in tension will become m by I into y b, that means m by z b, which should be less than or equal to sigma b t. Now, this at the bottom we are considering as tension and at the top we are considering as compression, assuming that suppose a beam is like this, moment is developing like this, then here it is developing, the beam is say moment is developing like this. Now, if it is buckled like this, so at the bottom it will develop top, at the top it will develop at the bottom it will develop tensile force and at the bottom side top side it will develop the compression force, right. So, what we are seeing, that here we are means the section is undergoing under compression and here it is undergoing under tension. However, it is not always true, because it depends on the type of moment, what type of moment is going to develop at that section. On that basis, the stresses, whether it will be in tension or in compression, bending stress in tension or bending stress in compression, that will be depending on the type of bending at that particular section. Now, as I was telling, y t is nothing but the distance of extreme top fiber, and similarly y b is distance of extreme bottom fiber. Z t we can write that section modulus with respect to top fiber, which is can be written as I by y t, I by y t. Similarly, Z b is equal to section modulus with respect to bottom fiber, which will become I by y v, and sigma b c is the allowable compressive stress and sigma b t is the allowable bending tensile stress, right, allowable bending compressive stress and allowable bending tensile stress. So, these are the things, means parameters which we know, from which we can find out the sigma c means compressive stress and sigma t, right. Now, for laterally supported beam, the allowable bending stress in tension and in compression is equal, that is sigma b c equal to sigma b t, which will be equal to 0.66 into f y. So, for laterally supported beam, remember for laterally supported beam, as per the Coral provisions, the sigma b c and sigma b t will be equal to 0.66 f y, where sigma b c and sigma b t are the allowable bending stress in tension and in compression, right. So, in this way we can find out the value if we know the grade of steel which we are going to use, right. And for laterally unsupported beam, the allowable bending stress in compression is limited by the lateral buckling of compression flanges. it is a function of relative properties of the section such as d by t, L by Le by Ry, then T by T ratio and dW by T ratio. These parameters I am coming later. So, what I am seeing here, that in case of laterally supported beam, the sigma Bt will become simply 0.66 Fy, but sigma Bc will be function of some parameters, right. Those parameters are d by T ratio, Le by R ratio, Ry ratio, T by T ratio and dW by T ratio. So, this is the difference which we will get for laterally supported and laterally unsupported beam. However, here we will focus only, today's lecture we will focus only on laterally supported beam. Here you see, as I was telling, what is d, t, capital T, small t, all these things. Let us see. Suppose if it is a I section, then say what you can do now. This is called D, capital D, where D is the overall depth of the beam. So, D is this which is required to know for calculating the allowable compressive stress due to bending in the unsupported beam, right. T is the mean thickness of compression flange, mean thickness of compression flange. So, if this is the compression zone, then this will be T. So, sometimes this also can become T if compression flange developing at the bottom. So, in this case, if compression zone is this one, then we can write that T is equal to this width, that the mean thickness of compression flange, and then small t is the wave thickness, this is called small t, and Le is the effective length of compression flange, effective length of compression flange, and Ry is the radius of gyration about y axis. If this is y, then we can say, and if this is x, then Ry is the radius of gyration about y axis, right. So, from these parameters we can find out the values of this d by T ratio, where d is the overall depth, T is the average thickness of the compression flange, Le by R ratio, Ry ratio, this also we know, T by T ratio and dW by T ratio we can find out. dW is the dW will be depth of the wave. So, in this way we can find out those ratio, and from that ratio we can find out the allowable compressive stress due to bending, sigma Bc, for laterally unsupported beam. So, in this way you can find out. Now, how do we find out? Some derivation is there which we will discuss in next class. In IS 800/1984, the steel design code, there we will get the value of sigma Bc for different ratio of d by T and other things, right. But that values have been calculated from some expression which also will show in next class. Now, to calculate these things, one important thing is required, that is effective length of compressive flange, effective length of the compressive flange. So, in clause 6.6.1 of IS 800, it has defined how to calculate the effective length, that has been specified in clause 6.6.1 of IS 800/1984. What it is told, that for simply supported beam and girder where no lateral restraint of compressive flange is provided, but where each end of the beam is restrained against torsion, the effective length L of the compression flanges shall be taken as follows. Okay. That means, when a simply supported beam or girder where no lateral restraint of the compressive flange is provided and where each end of the beam is restrained against torsion, the effective length can be taken as follows, which is given in the code. That is, with some different end conditions, the effective length has been defined in the code, right. Effective length has been defined in the code. That is, say, suppose in case of unrestrained against lateral bending, if it is unrestrained against lateral bending, then effective length can be taken as L, that means the clear span, the span length, right. and if it is partially restrained against lateral bending, then this can be taken as 0.85 L, right. If the end conditions is partially restrained against lateral bending, then we can consider as 0.85 L. Remember, this is for the simply supported beam and girder, where no lateral restraints of compressive flange is provided, but where each end of the beam is restrained, right. So, against torsion, third case is fully restrained against lateral bending, that will be considered as 0.7 L. Fully restrained against lateral bending will be 0.7 L. And if effective lateral bracing at intervals along the length is provided, then the effective length will become distance between intersection of bracing with the member. Distance between intersection of the bracing with the member. In fact, these are given in the code, which can be looked later by the readers. Again, where the ends of the beam are not restrained against rotation, against torsion, or where the load is applied to the compression flange and both the load and the flange are free to move laterally, the above values of the effective length shall be increased by 20%. So, above values of the effective length can be increased 20%, that means 1.2 into LE. Whatever LE value we are getting from the table earlier, that can be increased up to 1.2 L. When? Let me again reiterate, that is where the ends of the beam are not restrained against torsion, or where the load is applied to the compression flange and both the load and the flange are free to move laterally, the above values of the effective length shall be increased by 20%, right. So, that has to be taken care while calculating the effective length. Now, in clause 6.6.3, it is told that for cantilever beam, the effective length of the beam are as follows. For if we consider the cantilever beam, then effective length will be as given in the table. Now, for different end condition of the beam, the effective length has been considered. Say, in case of built in at the support with free at the end will become 0.85 L. Free at the end, it will become 0.85 L. Again, with restraint against torsion at the ends by continuous connection, in that case we will consider the effective length as 0.75 L. So, in this way we can find out the effective length. Now, this connection has been shown in figure A. In the codal provision, you will see this is the type of connection which has been made, that cantilever built in at support, restraint against torsion at the end. So, in this case the effective length will become 0.75 L. Now, in third case, the end condition is like this, that restraint against lateral deflection and torsion at the free end and at the end continuous, figure B, that will be 0.5 L. So, in figure B you see this length will become, effective length will become 0.5 into L, right. Cantilever built in at support, restraint laterally at the end. So, in this case the effective length will be this. Again, when unrestrained against torsion at the support and free at the end, unrestrained against torsion at the support and free at the end. In this case, in figure C it is shown that the L will become like this, right. So, if L1 is this, L2 is this and L3 is this. So, L will become 2L3 and here L will become 3L1. So, 3 times it will be, right. So, 3 times unrestrained against torsion at the support and free at the end. In this case, this will be 3L, and partially restrained against torsion at the support, in that case it will be 2L, which has been given here. See, in this case it will be 2L and in this case it will be 3L, right. So, for different end condition of the cantilever beam, the effective length has been calculated in different way. And number 6 condition is restraint against torsion at the support and free at end, which is given in figure E, that is this one. Cantilever span continuous at the support, fully restrained against torsion at the support and unrestrained at the free end. In this case, effective length will become equal to L. So, these are the some conditions where codal provision has been given, and through that we have to find out the effective length for calculating the sigma BC. Another thing is told in the code, that is, if there is a degree of fixity at the free end, the effective length shall be multiplied by 0.5 by 0.85, 0.5 by 0.85 with this ratio in case of 2 and 3 above, and by 0.7 by 0.85 in case of 3, 4 and 5. So, the cases 1 to 6 we have discussed, right. 1 to 6 we have discussed. In case of 2 and 3 we can multiply by 0.5 by 0.85, and in case of 4, 5, 6, this will be 4, 5, 6, it will be 0.75 by 0.85. Now, we will discuss about some criteria to find out the shear stress and the design value of the shear stress, right. As I told, that first step is to find out the appropriate section of the beam from the bending stress point of view. Now, what we will do, we will try to find out the what is the shear stress developing for that particular section and what is the allowable stress, allowable shear stress of that section. Then we have to see whether the developed stress is less than the allowable shear stress or not. If it is less than, then fine, it is okay, otherwise you have to increase the dimension of the section. In case of shear, what we will do, that we know that the shear stress developed in the section can be find out by this formula, that is tau v is equal to Vq by IV. How it develops? Suppose if we have a rectangular section, right, with say width as B and this is D, then we can find out the shear stress that will develop parabolically like this. This is the maximum tau max which is developing, say in this line the shear stress will develop this one, which is called say tau v, right. Tau v is the developed shear stress, and average shear stress can be found from here. That means with equivalent area if we make, this will be tau VA. So, this is called tau VA, and tau max will develop at the neutral axis, means at the middle, means during at the CG or somewhere else, means at the middle basically in this case, and it will be 0 at the end, right. So, in this way you can find out, and tau v can be expressed from this equation. Now, you see this tau v, the shear stress developed, is a function of not only shear force Vq by IV, that means is a function of Vqi and V. V is the width of the member. Now, if we increase the V, then what will happen? We will see the tau V is decreasing. That means, if we increase the value of V, if we increase, tau V will decrease. So, we have to try to increase the value of V at particular position, so that tau V becomes less. Suppose in case of I section, how it develops tau V, let us see. So, this is an I section, so this is the neutral axis. Now, if we see, we will see, now in this case Vq by IV, now it will start from 0 and IV, here B is this one, right. So, this will become something like this, then suddenly it will jump here at this, right. So, because B is reducing, so it will jump here and then it will develop like this. right. So, shear stress tau v will be developing like this. This is the maximum tau max. Here it is important to note that this portion is very less, shear stress is very less, because here B width of the section is very high, and sudden jump of means sudden decrease of width at this position is going to increase of shear stress suddenly. So, this is how it develops. So, you have to take care all these things. Here what are the parameters B Q by IB? As we know, B we have told already that width of the section at the point where shear stress is calculated. If we are calculating shear stress here, then we have to calculate the B here, and other thing is V is the transverse shear force which can be calculated from the loading condition, and tau V is the transverse shear stress, means due to the shear force developed, and I is the moment of inertia of the section. I we can find out. So, what we are seeing in case of developing tau V, V is constant for a particular section, I is constant, right, varying only V and Q. What is Q? Q is the first moment of the outer area about the point where shear stress is computed. Remember, first moment of the outer area about the point where shear stress is computed. Suppose we are computing the shear stress, say suppose here, so first moment of the outer area. So, from here we can find out, right. So, in this way Q value can be find out. Now, you see the moment you are increasing the value of means we are value of Q, then tau V will be increasing. That means, if you go below from the extreme fiber or go up from the extreme bottom fiber, then this area will become more. So, outer fiber means outer section area will become more, means this Q will become more, that means tau V will be becoming more. That is why maximum stress is developing at the center, right, where the maximum area of the sections will get from outer portion, right. That is why we have to remember that Q is first moment of the outer area about the point where shear stress is computed, right. So, in this way I can find out tau V. Okay. Tau V is the developed shear stress. Now, average shear stress in rolled channel and I section can be found from this equation, that is average shear stress is shear force by depth of beam into wave thickness. That means, some average shear stress for channel section and for I section can be found out simply from this equation, right. Or we have seen that how to find out the tau V average shear stress, that equivalent we have to make, right. Now, as per the clause 6.4.1, what it is told in IS 800 clause 6.4.1, that permissible shear stress tau Vm is equal to 0.45 Fy. Permissible shear stress tau Vm, that will be equal to 0.45 Fy, where Fy is the yield stress. That means, for different grade of steel Fy will be different. So, say suppose we are using Fe 250, so Fy will become 250, right. So, on that basis we can find out the permissible shear stress tau Vm. Again, for design purpose, the above condition is deemed to be satisfied if the average shear stress in an unstiffened member calculated on the section on the wave does not exceed the value of this. That means, simply we can calculate tau Va is equal to 0.4 Fy, right, and it should not exceed this value. So, average shear stress should not exceed the value of 0.4 into Fy. Another aspect is the bearing stress. Bearing stress, when it develops, as we know, where the concentrated load is there or where the support is there, suppose simply support is there. So, the stress will develop here, some because of concentrating force in nature, the stress will develop. So, bearing stresses are set up in the beam at places where concentrated loads or reactions act, right, and that can be found out from this equation. Sigma P is equal to P by AE. where P is the concentrated load in Newton, right, and AE is the effective area at the toe. AE is called effective area at the toe and P is the concentrated load in Newton, and this bearing stress should not exceed 0.75 Fy. This bearing stress sigma P should not be greater than 0.75 Fy, and this is defined in code IS 800 1984 in clause 6.3. So, regarding bearing stress, in clause 6.3 of IS 800 it is told that the bearing stress whatever it is developing, it has to be less than 0.75 Fy. That also we have to keep in check, right. So, if the calculated bearing stress exceeds the bearing value of 0.75, then what to do? Either the bearing block should be made longer or beams with a thick wave or bearing stiffness should be provided. So, possible remedy which we can do, that either we can use the bearing block or beams with a thick wave or bearing stiffness, that we have to provide. So, in this way we can manage, we can make the beam shape, right. So, from bearing stresses point of view we have to check this one. Another important aspect of the design of beam is the wave crippling, means we have to see whether the beam whatever we have designed is safe against the crippling effect or not. So, what is the wave crippling? Let us see first, that if say suppose say concentrated load is there, say we are making an I section, right. So, if it happens like this, that means because of concentrated load here, say P, here it is buckling, means crippling, right. So, the waves of the rolled steel sections are subjected to a large amount of stresses just below the concentrated loads and above the supports from the support. Large bearing stresses are developed below the concentrated loads. So, because of the large bearing stresses developed at the support and the below the concentrated load, so chances of wave crippling will be there. So, in case of support, how it will look, means how it will develop. So, if support is bottom, then say this will develop like this, something like this, right. So, wave crippling will develop here if we have support here, right. Now, we have to design the beam in such a way that this wave crippling can be restrained, right. So, to keep the bearing stresses within permissible limits, the concentrated load should be transferred from flanges to the wave on sufficiently large bearing areas. The root of the fillet is the most critical location for failure because the resisting area has the smallest value there. As the resisting area is becoming less, so chances of failure will be there. So, the bearing stress we can find out from this sigma P is equal to P by bearing area, where bearing area can be calculated from this B1 into T. That means, sigma P will become P by B1 into T, right. Now, what is B1 and what is T, I am coming later. So, first let me draw the diagrams from which I can find out the value of B1 and T. So, if we see the plate, this is at the support, now if support is here, we are going to provide say bearing here with a width of V, and here it is acting the load P, right. Similarly, if the concentrated load is here with a bearing plate of V with a load P, right. Now, it is assumed that the angle of dispersion of load will be 30 degree. So, these are the assumptions we made, right. That means, this is 30 degree and this is 30 degree. Okay. So, if angle of dispersion is like this, then I can find out this value, which is termed as B1, right. Similarly, in this support what will happen? Angular dispersion will be only in this direction with 30 degree angle. So, this will become B1, right, and the section is, say, suppose I section we are considering. So, this will look like this, right. So, this is the thickness of the flange, say maybe H2, right, and say this is H2 and this is the depth of the wave, say I can write D1, and the total depth or overall depth of the beam is D, right. So, we are assuming that the load is dispersing at a 30 degree angle. So, what we can find out? The bearing length B1, this can be find out for this case, say this will be B plus this much, that means B plus this much. This much means if this is H2 as told here. So, if this is H2, then this is H2. So, this is 30 degree. So, this will become H2 into root 3. So, H2 into root 3. So, in two places it is there. So, 2H2 root 3. This is under concentrated load. So, under concentrated load we are finding out bearing length B1 as B plus 2H2 root 3. Why it is required? Because to calculate this value B1T, right, to find out the bearing value, right. Another is bearing length B1 under means at support. At support how much it will be? Bearing length B1 at support, B1 will become B plus H2 root 3, because here only angle of dispersion is here. So, B1 will be this much, here there is no scope to disperse. So, in this case bearing length is becoming B plus H2 root 3, right. Now, here we can say that sigma P, which we are going to develop P by B1 into T. So, sigma P we can write that bearing stress, right, and say this can be find out in MPa if P is the concentrated load or reaction. In case of support it will be reaction, okay, from support in Newton, right, and then B1 we have. Now, T is the wave thickness in millimeter. So, this is Newton and this is millimeter, this is millimeter. So, we can find out the bearing stress, and H2 is the depth of the root of fillet in millimeter. So, we have to put the value in millimeter here H2 T, so that we can find out B1 also in millimeter we can find out, and then if P is given in Newton, so we can find out sigma P as MPa. Remember, chances of mistake will be there if we mismatch the unit. Unit has to be in same order. Again, whatever we are calculating the bearing length, that may be negligible or very small. Sometimes it may be very small, means in some cases the required bearing length may be very small and negligible, but in this case a bearing of minimum 100 mm length should be provided. So, in any case we should provide a minimum of 100 mm length of bearing should be provided. The value of the calculated stress should be less than the permissible bearing stress. Permissible bearing stress we have shown. So, in general it has been found that if the beam section is safe in crippling, it will be safe for buckling, right. When we are checking the crippling stresses, means if it is safe for crippling, then buckling also it will be safe, in general, but we cannot make it, means for all the cases we have to check. Buckling things I will come in next class in details, how buckling effect has been considered, how the stresses has to be calculated, and how the load is coming into picture due to buckling. All these things we will discuss in later, right. So, what we have seen, that a minimum bearing length of 100 mm has to be provided if the calculated bearing length becomes less. With that we can go for design, because in case of concentrated load or at the support, the chances of wave crippling will be there, because wave thickness is generally become very less in case of steel member. We have seen I section, we have seen channel section, we have seen other sort of section which we will be using. So, on those cases sudden jump of width from wave to flange is there. So, their chances of crippling will be there. So, to restrict those things, we must have to check whether the bearing stress whatever it is developing is capable of taking the load or not. Now, we will discuss the design steps for laterally supported beam. As I told that today we will be focusing our lectures on laterally supported beams. So, whatever we have discussed so far, let us make it in step by step, so that when we will go for one workout example we will be easily can do. So, what are the steps? What will be the step at the beginning? So, let us make step say 1, right. So, here what will make, let us say calculate the expected load on a beam. That means we have to find out what is the load coming into picture on a beam. Load means imposed load, dead load, and including the self weight. So, all this load has to be calculated, then we have to see what are the load is coming, and accordingly in next step what we will do, we will find out what is the maximum bending moment and shear force. So, in step 2 calculate maximum bending moment and shear force. The moment we are calculating the maximum bending moment and shear force, then we can find out the stresses due to moment. So, this maximum bending moment and shear force can be find out from the loading condition and from the boundary condition of the beam. So, from there we can find out. So, in step 3 we can find out that calculate section modulus. Section modulus required for the load and choose a suitable section. Suitable section from SP 6. So, from SP 6 we can find out. So, how do we calculate the section modulus? As you know, the section modulus Z can be written as m by sigma BC or sigma BT, right. Here sigma BC and sigma BT is same, which is 0.66 Fy. So, from this I can find out that what is the section modulus is required, and the moment we find out section modulus, this is required, then we can see what are the available section which is closer to the required section modulus. Then we can choose some suitable, so choose a suitable section. First we have to decide what are the availability of the section, whether it is I section is available or channel section is available or some other section is available. On the basis of availability, we can find out a suitable section. If nothing is given, as we know, the most efficient section for bending consideration point of view is the I section. So, we can provide some I section, where we can find out the closure value of Z section modulus, and the choosing means the required Z should be less than the applied Z. Whatever we are applying, whatever we are choosing, that should be little higher than the required one. Now, step 4, that is check for shear, right. So, I know that average shear stress can be developed from this formula V by D into T, and which should be less than 0.4 Fy, where T is the wave thickness and D is the overall depth of the section. So, in this way you can find out. And in step 5, in next step what we will do? Check for deflection. Check for deflection. So, as you know, in last class we have shown check for deflection means we have to see what are the deflection is coming, that should not be greater than span by 325, that means L by 325, span means effective length by 325. So, the calculated delta deflection should not be greater than this, that we have to check. So, how do we calculate the delta? That we know, we have shown earlier that for standard beam with standard loading condition with some boundary condition, we have seen that how delta is, means that KL, how the coefficient of deflection has been given. So, directly either from there or from calculation we have to find out what is the maximum deflection happening in the beam, and that we have to check whether this maximum deflection is more than the limiting deflection, that is span by 325. If it is more, then we have to redesign, otherwise it is okay. Next step is check for crippling. Step 6, check for crippling, right. So, here what we will do? We will find out sigma p is equal, means it should be less than or equal to 0.75 Fy, means allowable stress will become 0.75 Fy. So, developed stress, bearing stress sigma p should be less than 0.75 Fy, right, where sigma p can be calculated from this formula, that is P by B plus 2H2 into root 3 into T for concentrated load, right, and this will become P by B plus H2 root 3 into T at support. So, we will calculate the bearing stress developed at the support and at the concentrated load. If concentrated load is there, then we can find out what is the bearing stress is developing and whether it is less than 0.75 Fy or not. If it is less than 0.75, it is okay, otherwise you have to again redesign. And from this we can find out the value of V1, the bearing length, right. So, in this way, step by step we have to check and we can design a beam. Now, we will go through one example. Today I will give the example, means I will write down the example here, you try to do at your own time, and in next class I will solve the problem and we will see whether it is matching with your workout example or not. a simply supported steel joist with a 5 meter effective span carries a uniformly distributed load of 50 kilonewton over its span inclusive of self weight, right, 50 kilonewton per meter over a span inclusive this. The beam is supported laterally throughout. Select a suitable section and check its safety. That means, we will try to design a beam which has span length of 5 meter, that means the effective length is 5 meter, right, and a uniformly distributed load UDL, that is I can write W, right. So, that will become say 50 kilonewton per meter. Okay. So, these are the two things has been given, which including self weight. We are assuming that total load is coming 50 kilonewton per meter, which includes self weight, dead load and other things, and this is a simply supported steel joist. Okay. So, it is like this, simply supported steel joist, right. So, this has a UDL load of W is equal to 50 kilonewton per meter, and of course, the effective length has been given LE is equal to 5 meter. Okay. So, now you have to design the section. That means, what we will do here? Yes, another thing is the Fy value, the grade of steel we are going to consider is as Fy is equal to 250, because unless we know the stress, the permissible stress of the steel, we cannot find out, means type of steel we have to know, accordingly the stresses will be developing. So, where Fy here it is given 250 Newton per millimeter square. So, first we will try to find out what is the bending moment, means maximum bending moment. In case of simply supported beam, what will be the maximum bending moment? That will be WL square by 8, right. So, maximum bending moment we will find out, then we will find out the maximum shear force which is coming at the support, then what we will do? Then we will find out the appropriate section on the basis of section modulus. First we will find out section modulus, and as it is told that supported laterally throughout, so sigma BC will be equal to sigma BT, which will be equal to 0.66 Fy. So, from that we can find out. Next what we will do? That appropriate section on the basis of required section modulus we will find out. After that we will check for shear, right. So, maximum shear stress we will find out, from that we will find out whether it is okay from the developed shear stress point of view. Then we will go for deflection, how much deflection is happening due to this moment and what is the limiting displacement. If it is not okay, we have to increase the section, if it is okay, fine. Then we will go for check for crippling, means crippling effect we will see whether it is okay or not from the bearing length and other things. If it is okay, fine, otherwise you have to change the section. So, in this way step by step we will check. So, first we will find out and upon the basis of stress due to bending. From that we will first find out an appropriate section, then we will go on checking one by one shear, deflection and crippling, and after checking all the things it will be selected that particular section, then accordingly we will do, right. So, I hope you can do these things properly, and let us do, and next day I will work out this example and use I section, so that the answer will become same for whatever you are doing and whatever I am doing will become same. Let us use I section only here. Okay. So, with this I like to conclude here. Tomorrow we will discuss about the buckling effect and other things. First we will go through this example, then we will do other things. Thank you very much.